What's up, guys? This is Mr. Bond. Today we're going to run through the beginning of applications of derivatives, which starts with extreme values of functions in section 4.1, which is all about finding the maximum and the minimum on a graph. So we understand the idea of an absolute maximum as the highest value on the graph, or the greatest y value, the absolute minimum being the lowest value on the graph, or the lowest y value. So this idea is tied directly to what we call the extreme value theorem. The extreme value theorem states that if you have a continuous function on a closed interval, like the one that you see before you, then that function is guaranteed to have both a maximum and a minimum over the course of that interval. So looking at this function, if we just look at the x values as they're defined, there is a maximum at b, that's one of our endpoints, and there is a minimum at d. All right, so let's just start with a few different variations of the x squared function, just to be clear. If we have x squared defined over the interval -1 to 2, including the endpoints, here are some key points that I've defined. The extreme value theorem is satisfied here because this is a continuous function over a closed interval. We can identify the absolute maximum as being at 2, 4, and the absolute minimum is at 0, 0. It's a little bit more complicated when the function is not defined over a closed interval. So if we don't include those endpoints, the extreme value theorem is not satisfied. We can still observe the same function with open circles on the ends, and we can still note that it does have an absolute minimum at 0, 0. But what about the maximum? Well, you know that the maximum is pretty close to a height of 4. So does it have a height of 3.9? Well, no, because you can go higher than 3.9. You can go to 3.99. And then you can go to 3.999, etc., etc., etc. So because you could keep getting closer to 4 forever without ever reaching it, there is no absolute maximum defined because of that open interval. And again, we knew that there was a possibility of this because the extreme value theorem was not satisfied. If the extreme value theorem is not satisfied, you may still have a max, you may still have a minimum, but it's not guaranteed. Here's another adjusted interval. This time we're including the endpoints, but we're not including 0, 0. So again, the extreme value theorem is definitely not satisfied because this function is not continuous. Now, we can note that it absolutely has the absolute maximum. But what about the absolute minimum? Well, logically, again, we know that it should be close to 0, 0, but what is that exact height? It can't be 0.1 because we could go lower to 0.01, and then we could go lower and lower and lower without ever actually reaching 0, 0. So there is no absolute minimum on this graph. So our goal is to figure out where do maximum and minimum values occur on a function. And we want to use calculus to do that. So we note on any given function that maximum and minimum values can occur when we're either located at an endpoint on a closed interval, or we're located at a point where the derivative is 0, like points C and E here, or where the derivative is undefined at D. So if we were to take a function, find the derivative, set the derivative equal to 0, set the derivative equal to undefined, or observe where the derivative is undefined, I should say, and then also consider the endpoints on the interval by which the function is defined, then we should be able to figure out where we have maximum and minimum values. A local extrema is a possible max or min value over the course of a function. So if we're given the fact that C is some local extrema on a graph, then we have to know that at x equals C, either the derivative is 0, which means that you have a horizontal tangent, or the derivative is undefined, which means that you have some sort of a cusp or a corner. So essentially, as we piece this process together here, if our first derivative is 0 or d and e, then C is a critical value. And we must examine the critical values and the endpoints of the function in order to determine where our absolute maximum and our absolute minimum occurs. The absolute extrema on a graph are the maximum and minimum values. To find them, we want to find the critical values. The critical values are all the places where the first derivative of the function is either 0 or undefined. So step 1 is essentially everything you did in chapter 3, finding derivatives of various functions, and then doing a little bit of algebra to solve them. Then we need to evaluate all those critical values, finding their y values and comparing. We also want to make sure we include the endpoints if it is a closed interval. You can set up a table to compare the different y values, and then pick out which one is the largest, that's your maximum. Pick out the smallest, that's your minimum. So let's try a few examples. All right, so let's go through this full process. We want to find the extrema for our graph. That means we want to find the max and the min. We have a function defined over the closed interval -1 to 3. Let's first start by trying to find the derivative function. Go ahead and pause the video and then unpause once you've found the first derivative. All right, so the first derivative is 2 minus 2x raised to the -1/3. And now what we need to do is figure out when is that thing 0 and when is it undefined. Well, it's undefined at 0. We can figure that out pretty easily because if we re-express the function, the second term is 2 over the cube root of x, so we can't have 0 in the denominator. And when is it equal to 0? Well, we can just set the derivative equal to 0 and try to solve that thing. I think the most efficient way to do that is to pull out a 2, and then note that 1 minus x to the 1/3 will be 0 when x is equal to 1. So I ended up with 2 critical values. You could end up with any number of critical values, but we ended up with 2. Critical value at 0, critical value at 1. So we are going to have to compare the y values for those critical values as well as the endpoints on our function. So we're going to put a little table together here. So I include my critical values and I include my endpoints. Note the fact that the endpoints from -1 to 3, 0 and 1 are included in that interval. If your critical values are not within your interval, then you don't need to include them in your table. And now I just need the y values. Now, the y values, be careful, make sure you plug into your original f of x function. So I'm going to go ahead and do that. Now, we end up with one ugly y value here, but we can kind of deduce the cube root of 9 is roughly just above 2, right, because it's greater than the cube root of 8. So 6 minus 3 times a number that's just bigger than 2 should give us something that's negative, but pretty close to 0. We don't actually need to know the exact value because we're just trying to figure out what the largest y value is, which is 0, and what the smallest y value is, which is going to be this -5. So therefore, now we can make a conclusion about our original function f of x. F of x has an absolute maximum at 0, 0, and an absolute minimum at -1, -5. All right, go ahead and try to find the critical values for this next example. Note the open interval. That just means that there's not a point at 1, but we should still look at what's happening at 1 so that we can properly assess our max and mins. Go ahead and try it. All right, so we find that there is never a place where the first derivative is 0, and it's undefined when x is equal to 0, which is between -3 and 1. So we set up our table, and we observe our y values. Note that the fifth root of 9 is greater than 1. Therefore, the fifth root of 9 is where we have an absolute maximum, and 0, 0 is our absolute minimum, and we can write a little conclusion. The reason I said that the fifth root of 9 is greater than 1 and that gives us an absolute maximum is because we knew that we have that open circle on the endpoint, or the lack of an endpoint, at 1, 1. So if the fifth root of 9 had been a number that was less than 1, then think back to when we were looking at the x squared example, right? The open circle would have been higher up, but we wouldn't have been able to define precisely where the absolute maximum was. All right, last example. Go ahead and try this one. Try to find the critical values first. We got a little chain rule, we got a little trig. Unpause when you're ready. All right, so our function is never undefined. We know the behavior of a cosine graph. And when we set the first derivative equal to 0, we find that cosine x pi is equal to 0. Therefore, x pi has to be pi over 2 plus 2 pi n, or 3 pi over 2 plus 2 pi n. divide through by a pi because we're trying to solve for x. We end up with x equals 1/2 plus 2n, or x is equal to 3/2 plus 2n. Keep in mind our interval by which our function is defined, from 1/3 to 1. We can't really use any of those two n's, right? We need n to be equal to 0 in the first case in order for it to fit within that interval. And there's never a place in which 3/2 plus 2n will fit within that interval. So we only have one critical value here. It's just at 1/2. I can go ahead and set up my table. And we're going to include those endpoints in the table. So we have 1/3, 1/2, and 1. And we have the y values for all of those. The absolute maximum occurs at 1. The absolute minimum occurs at 0. So I could write a full sentence saying, okay, the absolute maximum on this graph occurs at the point 1/2, 1, and the absolute minimum on this graph occurs at 1, 0. I hope this was useful as you guys go through section 4.1, observing extreme values.